Hi, this is Mark Weitzman. Welcome back to my YouTube channel on theoretical physics. I'd like to do, this is quantum field theory, a student's perspective. And I want to do a lesson 5. Mark Signicki's book on the LSZ, LSZ. This is named for 3 people, the initials, reduction formula. Now, this is one of the key formulas in QFT, and Signicki treats it a little earlier than they do in most books on QFT. But I like his treatments, not so much, every book sort of like fudges when they derive this formula, and the derivation isn't that important. It's nice to follow and go through, but whether it's really sound or not is another thing. You would have to use like axiomatic quantum field theory to really get a decent derivation. But what is important is the result. And the way Signicki does it, he also integrates sort of like the beginning of renormalization into it, which is what I really like about his book. Most books on QFT, they don't really talk about renormalization until they calculate some Feynman diagram and they get infinity. And then they say, oh, okay, we need to renormalize. So he does it, he integrates it from the very beginning, because even if there are no infinities, you need to renormalize. Anyway, I'm just trying to understand my interface here. It's not. So what I want to do is to go through his derivation, and mostly I'm going to follow him very closely to what he does in the textbook. And I'll just write down a lot of equations and don't worry about whether the derivation is kosher or not. So let me start by reviewing some prior formulas that are used in the textbook. And we have the definition of a single particle state operating on the vacuum or the ground state. Then we have the definition, or the way to express these creation and annihilation operators in terms of the fields. And we use a standard definition here. The annihilation operators, of course, annihilate the vacuum. The vacuum is normalized. And the single particle states have a a delta function normalization with a few extra factors to make it. This is the Lorentz covariant normalization. Okay. So Sugnecki begins by defining time independent. And by the way, that's only in the free field theory. Localized states in momentum space near, let's say, a vector k1, and in position space near the origin. So he defines A1 dagger, and the 1 refers to the K1. It's defined to be the integral of D3K F1K A dagger K. So we're integrating, we're smoothing, where F1K is sort of like a Gaussian in momentum space. But this is what the 1 refers to, this K1. Okay. So in a typical two-particle scattering experiment, we're going to have an incoming particle state. The limit as t goes to minus infinity. A1 dagger t, A2 dagger t. I just want to check that I have this equation. Yeah, t goes to minus A2 dagger t. Need to change that in my notes. I left off the minus sign there. A2 dagger t acting on the vacuum. And our final state is equal to the limit t goes to infinity of A1 prime dagger t, A2 prime dagger t. So we have like incoming particles with K1 unequal to K2, so they're not collinear. Normalized states, II equal 1, and K1 prime is unequal to K2 prime, and normalized outgoing states. And we need to find our goal the overlap between F high. Okay. Now through various manipulations of calculus and algebra, things like integration by parts and the fundamental theorem, etc. Nothing deep. And I'm not going to show it here, just see equation 5.10 of the book, or the freely available online draft. God, Jesus. This is unbelievable. We obtained the following equation. Put an asterisk next to this one. It's a very important equation. Okay. Minus I, the integral d3k of f1k, the integral d4x e to the ikx, minus the partial squared plus m squared phi of x. Now, in free field theory, the right-hand side is equal to 0 because of the Klein-Gordon equation. But in the interacting theory, for example, with a 1,6g phi cubed interaction, we have instead just from your usual Lagrangian mechanics, and non-zero right-hand side. See, the whole problem with quantum field theory is that once you have interactions, particles are never really free. Even when they're far apart at infinity, they still have like self-interactions. And these self-interactions are responsible for renormalizations. So it's always like difficult to separate out the interactions from the fields. Anyway, that's sort of what's the problem with, you can try and do it rigorously, but it's not easy. Anyway, if we rearrange star, put that in the box. If we rearrange that, we're going to get A1 dagger minus infinity is equal to A1 dagger plus infinity plus I, the integral d3k f1k, the integral of d4x e to the ikx minus partial squared plus m squared, acting on phi of x, and the Hermitian conjugate, which you also need to rearrange, And this one you'll get A1 plus infinity is equal to A1 minus infinity plus I, the integral d3 k f1k the integral of d4x e to the minus ikx partial squared plus m squared phi of x. Also, by definition, if we just substitute in the matrix elements fi, I think above earlier we had these definitions over here, and so if I substitute those in, we get that this is equal to 0, a1 prime, plus infinity, a2 prime, plus infinity, a1 dagger, minus infinity, a2 dagger, minus infinity, 0. Now, if you notice, this is in time order. Remember, time order means that the latest times are on the left, the earliest times are on the right. So the earliest times are minus infinity, and the latest times are plus infinity. So you can see this is already in time order. So it's legal for us to just put a t in here. It doesn't change anything. Now, after we put that t in there, I can insert the, I use these equations over here. Let's call these star star. I use these equations. I substitute in for the values, and now what happens is, like, let's say I have a1 dagger minus infinity. I'm going to get a a1 dagger plus infinity, but that's going to go all the way, by the time ordering, that's going to be all the way over here, and it's going to annihilate to 0. Similarly, when I put in a1 plus infinity, I'm going to get an a1 minus infinity, which is going to go all the way here and annihilate to 0. So this is good, because now we're going to end up getting also according to Sebnicki, we no longer have to worry about wave packets. He doesn't exactly spell out the reason why, so to me this is a little bit of hand waving. But we can take sigma goes to 0, and f1k goes to del 3 k minus k1, and we get the delta function normalization. So now when you do all this substitution in here, when you put these equations in here, take account the time ordering, you end up getting the LSZ formula. So LSZ. And we get I'm going to make it a little bit more general. I'll explain that in a second. I to the n plus n prime. I'm going to have d4x1 e to the I k1 x1 minus the partial squared plus m squared. And then for every additional incoming particle, we have another term like that. And then for the outgoing particles, and again, additional terms for extra particles, all acting on this matrix element. Time ordered phi x1, phi x1 prime. And we so this assumes we have n incoming particles and n prime outgoing. Let me box this because it's so important. So again, if you had, let's say you have two particle scattering, then you'd have like n equals 2. You'd have a k1 incoming particle, then you'd have another term with k2, and then you'd have two outgoing particles, n prime, but it doesn't have to be that way. You could have two phis come in, and depending on the interactions, 4 or 6 phis go out, so it depends. But this is the outgoing particle terms. And this is the crucial, the most important object in quantum field theory. It's the matrix element between the ground state of the time-ordered fields. And a lot of what we'll do with Feynman diagrams upcoming in the next few weeks and path integrals is calculating this matrix element. And we'll find out that these other things here will like peel off, but that's in the future. So this is the first video. I think I'm going to stop here, and no, I'll continue with this. Might as well finish it in one video. So our derivation is definitely shaky. And probably one of the worst things we did was we assumed that the free field creation operators work in the interacting. They work the same way in the interacting theory. And Shinnecki says this is very he uses the words rather suspect. So let's just review the the physical eigenstates that we expect of the interacting theory. Okay, first There's a unique ground state. We're calling 0. And it has 0 energy and momentum. Okay. Very few people have problems with this, but maybe later on there will be problems. 2. The first excited state is a single particle state with mass m and arbitrary 3 momentum. K. And the energy, which we usually denote by omega, this is equal to the square root of k squared plus m squared. Okay. Now, the next excited states has 2 particles, and we're going to assume that there are no bound states. And of course, this is nonsense. You know, we have like hydrogen atom is a bound state of a proton and electron. It might not be the best example, but positronium, in a sense, is a bound state of an electron and a positron. It decays after a short while, but relative to its natural time scale, it lasts a long time. So, you know, and when we deal with quarks, and we have 3 quarks, we have bound states that last forever. You know, a proton is a bound state of 3 quarks. So one of the major flaws of quantum field theory is that it doesn't do good with bound states. There are ways to treat bound states, and like Weinberg does it in his book and everything, but most quantum field theory textbooks, they just ignore bound states. So in any event, what I want to do is pretend that there are no bound states. Then the lowest possible energy is 2m. This would be like when the particles are just like standing next to each other. They're not moving. They each have like 0 momentum. But you can have 2 particle states where there is relative momentum. And then we get a continuum of a 2 particle and more particles states. So I'll just draw the same diagram that is in the book. Let's say this is like the momentum, and this is like mass m. Then you get like a hyperbola through m. That's the single particle state. This is the energy axis. And then we get like through 2m, we also have the a hyperbola, but now it's not isolated. All these other states over here, this is the continuum. These are all possible. We can get, I don't know why it did that. Unbelievable. All right, let me do it again. So this is the isolated hyperbola through the single particle state. And then we have a hyperbola through the two particle state. And then we have a continuum, I guess. That's the continuum. Okay. So let's evaluate some matrix elements. So if we have something like, this is a formula, phi of x. This was used in chapter 2 of the book. This is the energy momentum operator. This is the relativistic generalization of the Heisenberg equation in quantum mechanics. In quantum mechanics, we would just deal with like the energy. This would be replaced by E, and this would be X would be replaced by T. So we just get ET, and E to the minus IET, and E to the IET. X sort of goes along for the ride. Now, we could take the matrix elements 0, phi x, 0. So this is equal to 0, e to the minus I, px, phi 0, e to the I, px, 0. Is equal to 0, phi 0, 0. And since the vacuum has no energy momentum, you just expand this out exponentially, and you can see that that works. So now this number, this 0, phi 0, 0, this is just a Lorentz invariant number, and we want it to be 0. That's what it is in the free field theory. And, phi 0 contains these let's say, A1 dagger plus or minus infinity term operators are in the phi. And we want it to create only single particle states. We don't want it to create, if we got a number that's not 0, it would be creating some overlap with the ground state. With the ground state. Now, so if let's define V, because it's like the vacuum expectation value of the single field. If 0 phi 0, 0 is not equal to 0, then we can shift phi. That's just like renaming it. Okay, so we're going to replace in the Lagrangian we're going to have phi goes to phi equals phi prime plus V. And then the expectation value of phi prime is equal to the expectation of phi minus v, which is equal to 0. Okay, and then we rename phi prime by phi. So now we satisfy what we want. We have the vacuum expectation value is 0 of the field. And this is sort of like sort of the beginning, in a trivial way, of renormalization. Now, in the same way, we can look at the a one-particle state matrix element. Again, just applying, this to that leads to taking that out. Now this is again a number. It's a Lorentz invariant scalar. You could argue it depends on p, but the only Lorentz scalars are p squared, which is equal to minus m squared. So this matrix element just depends on m squared and maybe some other parameters in the Lagrangian. Now we want this to be 1. Because we want, again, we want the creation operators to create a correctly normalized one-particle state. Now, if it's not equal to 1, simply rescale phi by a multiplicative constant. So we're kind of assuming that it's not 0. Probably that's not too hard to justify. Anything but 0 is okay. We can rescale it. So the rescaled obeys so this is you might have heard about multiplicative and additive renormalizations. That's what we're sort of doing right now. Now when we get to the multi-particle state matrix element, it's just denoted as in a general way as having a total momentum of p, and n is all the other things about relative momentum and number of particles and everything. Czernicki shows, using the Riemann Lebesgue lemma, that we don't have to worry about it. Basically, the overlap with the vacuum with ground state and one particle state goes to 0. Again, you can read about this in the book on page 40 for details. So, to summarize, we start with a Lagrangian, our usual free particle Lagrangian, with interactions. Here it's like a phi cubed interaction. And then we shift and rescale phi to obtain. And you can see when you shift the constants and everything, and with the phi squared and the phi cubed, that you're going to get the following Lagrangian. I'm not going to evaluate what the z's are in terms of the shifts, but you're going to end up getting something like this: 1/2 z phi. Z phi is just a constant. See, the shift doesn't do anything with the partial derivatives because the derivative of a constant is 0. So this is just a multiplicative renormalization. It's like phi goes to z phi to the 1/2 phi. That's why we get that term here. And we have minus 1/2 zm m squared phi squared. Now the zm, we're going to get part of it now. Here the shift matters, but it only will contribute to linear and constant terms. And so the again, the zm is going to be, but it's also going to combine with the last term, so I can't evaluate it like that so simply. Plus 1/6 g phi cubed. So you can see when we, I'm sorry, and there's a zg in here. And then we're going to end up getting, when we expand these linear terms, we're going to get a quadratic term in phi, which goes into the zm. We're going to get a linear term, which goes into here. And we're going to get a constant term, which we can just drop from the Lagrangian because that doesn't mean anything. And so there's 4 constants, 4 unknown constants: z phi, zm, zg, and y. And our renormalization conditions they give us 2 conditions. So where do we get the other 2 conditions? The remaining come from requiring certain physical conditions. So we want the mass m, that should be the mass of the particle, and the way this works, and we'll see this in future lessons, the way this works is we're going to compute the mass in perturbation theory, It's going to be a whole mess thing of all these constants and the parameters, and then we're going to set it equal to m, and that gives us another relationship between these constants. And then the final constant that we have to, last condition, so that's one condition, and then finally we'll have a condition on the scattering amplitude. That so that it depends on G in a specific way. I know this is vague, but you'll see when we do it later that will require, like, you know, when all three particles are like on shell or something, we get a certain scattering and so on. In as an example for this, in quantum electrodynamics, the constant E is defined so that the low energy Coulomb scattering goes as is proportional to like e to the fourth with definite constants. Definite constants of proportionality. That helps determine like the final condition, and happens to agree with the classical calculation of scattering at low energy. So that's all I'll have to say for now about LSZ. The main thing is you be comfortable with the actual LSZ formula, which I have in a box up above. This is the main thing. And you'll see how this is implemented. You know, we'll end up, the next lesson we're going to do is the Feynman path integral, so we can calculate these matrix elements. And then we'll go to like Feynman diagrams and show how to get the scattering amplitudes and then turn them into cross sections and compare with experiment. So it gets more interesting as in the next few lessons. We'll actually be doing some Feynman diagrams. I'll see you next time. Thank you very much for watching. Bye-bye.